So in the earlier video, we talked about the fact that alkanes are very highly used as fuels. All right, but besides fuels, they're a very they have relatively limited use. All right, and that's because they're very unreactive. All right, so whenever you want to turn an alkane into another type of compound, you really don't have a whole lot of options. And perhaps the only useful synthetic reaction is what's called a free radical halogenation. So first of all, what's a free radical? A free radical is any molecule that has an unpaired electron. All right. So I'll show an example of that in just a second. All right. So when talking about free radical reactions, I want to bring up this one little convention that we use when drawing free radical reactions. So if you remember a while back, we introduced this method of using an arrow to show the direction of movement of electrons. All right. So if I showed this chlorine molecule right here, and I showed the electrons going from the bond to this chlorine. All right. If you remember back, then what that meant is to say we're going to take the electrons that are in this bond, and they're both going to go onto this chlorine, all right? And that's going to create 8 electrons, or 4 pairs of electrons around this chlorine, and 3 pairs around this one, because the electrons that were being shared are now on this chlorine right here. All right, that's what's called heterolytic cleavage, all right? Heterolytic cleavage is when the electrons move as a pair, all right? So you've got a pair of electrons, and they both go to this one, and so the other one doesn't have any of that pair anymore. All right, the opposite of that is what's called homolytic cleavage. All right, and the way that you show homolytic cleavage is in the style of the arrow that you use. All right, notice when we did heterolytic cleavage, the arrow had these 2 prongs on the arrow. With heterolytic, you do a single prong like this. All right, and so what this is going to mean is that in this pair right here, one of the electrons is going to go to this one, and one is going to go to the other chlorine. All right, so that we can show this like this. All right. One thing that I'm going to point out is that when you do these arrow pushing steps, a lot of times people are going to take some shortcuts. Not necessarily shortcuts, but you get to the point where you assume that the person looking at it knows what you mean. All right, so when I showed this right here, notice that there's one unpaired electron. All right, and a lot of times you're going to see people represent this just like this. All right, notice that so how would we know that there's 3 other pairs on this, all right, if we're not told? Well, it comes from the fact that there's no charge drawn here, all right? So when you look at this, what they're trying to indicate is, hey, there's one unpaired electron with that chlorine, and you notice that it's neutral, all right? So therefore, you would be able to figure out that there actually are 3 lone pairs on this chlorine that aren't drawn. All right, let's compare that to these guys over here. Notice that when you have 8 electrons around the chlorine, that would have a negative charge. All right, that would be a chloride ion. All right, so a lot of times you're just going to draw that as a Cl minus. All right, and the person would recognize that in order for chlorine to have a chlorine atom to have a negative charge, it would have to have 4 lone pairs around it, or 8 total electrons. All right, this guy right here, and if we do that formal charge calculation, you figure out that if it's only got 6 valence electrons, that would have a positive charge. You could represent that like this. All right, and so again, the person would say, well, how many electron pairs would chlorine have to have in order for it to have a +1 charge? And you could figure out that it would have to have 3 electron pairs. So just keep in mind that when we're doing these mechanisms, and we'll be doing some more mechanisms in this unit, a lot of times we're going to be using shortcuts where we just show this rather than having to draw in all of those lone pairs. All right. So this is the first reaction where we're going to talk about a mechanism. All right. And a mechanism is a step-by-step sequence of elementary reactions that comprise an overall reaction. All right. And if you remember back to kinetics, we talked about elementary reactions versus overall reactions. All right, so what I'm going to do here is there's actually 3 different parts to this mechanism. There's what's called initiation, propagation, and termination. All right, and I'm going to show each thing two different ways. All right, and I meant to write it here, but this column, if you draw a line like straight down through here, everything on this side right here would be what you'd be expected to know at the SL level, and things over here I'm going to be drawing in the arrow pushing, and this would be an HL topic right here. Okay, so the first step is initiation. All right, and initiation is just the step that's necessary just to get this started. All right, so what's going to happen is if you take a chlorine molecule and you irradiate it with ultraviolet light, what that's going to cause is heterolytic cleavage. All right, and I've shown that over here. All right, when you take this molecule and you shine UV light on it, it's going to cause this bond to break in a heterolytic fashion, where you're going to end up making two of these chlorine free radicals. All right, so what happens next is what's called propagation. All right, so one way you can think about it is that a chlorine radical is going to react with this is going to be methane. All right, and that's going to abstract one of the hydrogens from the methane to make HCl, but that's going to leave this right here, this is a methyl radical as a product. All right, what is then going to happen is that methyl radical is going to react with some of the original chlorine. All right, and that's going to make this molecule right here, which is chloroethane. All right, along with a chlorine radical. All right, and if you notice, this product, this chlorine radical, is the exact same material that we used as a reactant in this reaction. So the chlorine radical that gets formed in this step ends up being used as a starting material and can react with another methane molecule, doing this, creating the methyl radical, which reacts with chlorine, creating the chloromethane and the chlorine radical. All right, so this process right here can just keep on going forever. All right, if we're doing this as the mechanism, all right, or using the electron pushing, all right, what I've done here is I've just shown methane, where I've drawn one of those carbon-hydrogen bonds. And what we're going to show is one of the electrons is going to pair up with that single electron from the chlorine, and that's going to make the HCl molecule. All right, well, the other electron that was in this bond is going to go onto the carbon, and that's going to make the methyl radical. All right, the methyl radical is going to react with a chlorine molecule. Again, the same type thing. And remember, notice the way that these arrows are being drawn. They're only being drawn with that single wedge side. All right, so the thing that's going to cause this reaction to stop is what's called the termination step. All right, and whenever you have a termination step, it's always going to be the same thing. Two radicals are just going to pair up with each other and become a neutral molecule. All right, so there's three types of termination reactions you could have. All right, so if you take a look at in these steps here, what type of radicals did we have? We had a chlorine radical, we had this, and we also had this methyl radical. Well, two of your chlorine radicals could pair up to make a neutral chlorine molecule, and that would cause this chain reaction to stop. All right, another thing that could happen is chlorine radical could react with a methyl radical, and that could make this, which would cause a reaction to stop. Or two methyl radicals could pair up, and that would make an ethane molecule. All right, so again, this right here just shows the electron pushing forms of these reactions right here. All right, and last thing I wanted to point out is this would be the way this happens if we were desiring chloromethane as our one single desired product. All right, but one thing that's going to happen whenever you do reactions is a lot of times you're going to get undesired byproducts. And I'm just wanting to point out that this radical halogenation reaction it's a very messy reaction, because it's very difficult to only get one desired product. And that's because there's a lot of possible other side reactions that can occur. All right, so for example, notice one of the things that gets made in this reaction is this chloromethane. All right, well, I've drawn a chloromethane right here. And if you're doing this reaction, would that thing be in the presence of this chlorine radical? All right, this chlorine radical is going to be hanging around. All right, and this chlorine radical, where instead of reacting with the methane like we showed in these propagation steps, well, could it react with this guy right here? And that is indeed something that could happen. That would create this chloromethyl radical, all right, along with HCl. And that chloromethyl radical could react with chlorine, just like we had in this step right here, where we were doing it with the methyl radical. And if that were to happen, we would end up making this molecule right here. And this is, you could call it dichloromethane, but a lot of times it's called methylene chloride, which is a solvent that, you know, it's very common. It's what some people are using on their in their IAs. So the thing is, when you irradiate chlorine gas with methane, you're not just going to fish out one single product at the end. You're probably going to get a mixture of several different products, and you just separate them at the end of the reaction.